talk about the greatest experimental mathematicians of our time who passed away on January 7th. His name is Herbert Saul Wilf. But everybody called him Herb. He was ahead of his time all the time. He was first interested in astronomy. His first love was not mathematics, but astronomy. When he was 13-year-old, his parents bought him a telescope, and his first publication is when he was 14-year-old in 1945 in Sky and Telescope. He reported a solar eclipse. Also, according to his son David, he told me a funny story about Herb. He was already a prodigy, and he read Albert Einstein's popular book on relativity, and he found a mistake. And he wrote Professor Einstein and said, "Dear Professor Einstein, I really enjoyed your book, but in page 55, line 3, x squared should be x cubed." And then a couple of weeks later, Einstein wrote him a letter back. "Dear Mr. Wilf, thanks for pointing out this error. It will be corrected in the next edition." So what do you think Herb does with this letter? He doesn't save it, so his grandchildren can auction it later on and be very rich. He cuts the autograph out and pastes it on the book. So this was his missed opportunity, and maybe that's as well that I became a professor, because he had to make a living. So he did not have that respect for Albert Einstein. And his lack of respect to Albert Einstein came again much later, a few years ago, when he wrote the great essay in this great volume edited by Tim Gauss, Mathematics, the Princeton Companion to Mathematics. Tim Gauss initially asked him to contribute the essay on algebraic and numerative combinatorics. But modestly, Herb declined, so I got asked to do it. But instead, Herb asked Tim Gauss for permission to include an essay on experimental mathematics. So thanks to Herb, this summary of 20th century mathematics includes a short 5-page essay on experimental mathematics. So Herb really realized that the future of mathematics is experimental mathematics. And here how it starts. Once again, taking issue with Albert Einstein. Albert Einstein once said, "You can confirm a theory with experiment, but no path leads from experiment to theory." But that was before computers. In mathematical research now, there is a very clear path of that kind. It begins with wondering what a particular situation looks like in detail. It continues with some computer experiment to show the structure of that situation for a selection of small values of the parameters, and so on. By the way, his essay is a free download from his website that hopefully will exist for a long time, hopefully forever. And like all his papers and most of his books, he was a pioneer in sharing of information. And he founded the Electronic Journal of Combinatorics, a free journal that never passed a penny. It was all volunteer and was never passed a penny. And it was the first full-fledged electronic journal. So that was one of the very few pioneering things that Herb did. And he was really a visionary. He was ahead of his time, as I already said, and as his beloved wife, Ruth Wilf, said, who was married almost 60 years, but didn't make it to 60, 59 and a half years. Herbert Wilf commented that for Herb, everything was, not everything, sorry, teaching and research were intertwined. It was not only like most people, they teach, some people are better than others, and to research, some people are better than others, but it's usually disjoint activity. For Herb, teaching and research were intertwined. But not only teaching and research, so many things that are usually disjoint, so many dichotomies, sorry. Applied and pure. He was not a pure mathematician, he was not an applied mathematician. He was a mathematician, period. Discrete and continuous. He was not a discretian like I am, he was not a continuous, he was both. For him, continuous and discrete were one of the same thing, or two sides of the same coin. Conceptual and computational. Most computational mathematicians do not care much about conceptual things. They look down on conceptual mathematicians doing abstract nonsense. And vice versa, even worse. Most conceptual mathematicians very much look down on computational mathematicians, seeing it as routine, tedious computations. They have no notion about the effort that goes into it. So we have this mutual disdain between computational and conceptual, unfortunately, today. But for him, they were both one and the same thing. He was good at both. And Tim Gowers, the same guy who edited this, once wrote a nice essay about problem solving versus theory builders. He claimed the mathematicians can be divided roughly into two types, problem solvers and theory builders. Theory builders don't care about problems. They think problems are just puzzles, they're trivial, and problem solvers don't care about theory. They think they're boring, that's abstract nonsense. And once again, usually they look down on each other, with some exceptions. So Herb was both. He was a great problem solver, but he was also a great theory builder. So it was really a visionary, way ahead of time. He also saw the big pictures. He wrote a classic essay called What is an Answer, which everybody should read. It was in American Mathematical Monthly in the 70s. I have it here. I have it here, nice paper. He wrote, here. He also, it's dedicated, he wrote a dedication to Z, who knows exactly what an answer is from W. So that was nice of him, but he even knew better what is an answer. So it's a classic essay from 1982. American Mathematical Monthly, 1982. What is an answer? And he answered this question very good well. Many times, people don't know what a good answer is. And they publish lots of rubbish. Of course, he was a nice guy, unlike myself, and he never mentioned any names. But he just mentioned that quite a few papers, the answer, in this case to a combinatorial problem, is not satisfactory. So example, the enumeration. In enumeration, you have a set of objects, and you want to count how many elements. So there is an obvious formula, the caveman's formula. You just count it. You construct a set and count it one by one. And he was once asked to referee a paper with a formula, quote unquote, for the number of Latin squares. And he noticed that the formula to compute it takes much longer than the caveman's formula. So this prompted him to write this classic article, What is an Answer, that it should be read by anybody, especially in combinatorics. So he was really knew the essence of things. But I want to focus on two beautiful, he did so much, there's no way I can tell you everything he did. So I'd like to focus for posterity that of two of my favorite things that he did. Both of them, by hindsight, like all great mathematics, almost trivial, but not a priori. One of them is in collaboration with Neil Kalkin, the Kalkin-Wilf tree. So it's a family tree for rational numbers or fractions. And they have a classical paper called Recounting the Rationals. It's also mentioned briefly in the essays that I mentioned in the book of Companion, Recounting the Rationals. We all know that the set of rational numbers was written Q, or in more less technical language, the set of fractions, is countable. Unlike the so-called real numbers that are uncountable, they have Aleph of them, the set of rational numbers, even though it's much bigger, it's a superset of the set of integers, is countable. Meaning, you can line it up one by one. The first rational, the second rational, the third rational. But there was no satisfactory construction of this. And what Neil Kalkin and Herbert Wilf did was a beautiful family tree of fractions. Here goes. The very, very top, Eve or Adam, is 1. So whenever it's an integer, you write it as, for example, 5 divided by 1. So, very, very simple rule. It's so simple. But before telling you how to do the family fraction of, the family tree of fractions, let me describe how you draw a family tree of people. So let me give an example in Herb. So Herbert Wilf have 3 wonderful children. So you have 3 children. Susan, David, and Peter. And each of them also have children. Susan has only one child, but a very smart one called is Alex or David. Let me make sure. And that's taking out Michael. David has 3 children, all very, very bright and nice. Sarah, Rachel, and Alex. By the way, Alex is named after Herb's father, Alexander Wilf, also a very interesting man. And Peter, so far, has 2 children, Eva and Rosa. So here the typical short family tree of a human being. This vertex has 3 children. This has 1, this has 3, this has 2. So a person can have any number of children, in principle none, up to infinity, but in practice maybe up to 20. So this is the family example of a family tree. Also, for people, there's an extra complication that you have a wife or husband. So it takes 2 to have children. So what's nice about fractions, you don't need to get married. You can have a family trees. So let's construct now the family tree for fractions. And the rules are extremely simple. All you have to do to remember the following rule. From these rules, how to make children for a fraction, you can construct the whole tree all by yourself. So let me tell you the beautiful rule, which is, by the way, in this t-shirt. And this is a Kalkin Wilf tree. So every fraction, by definition, has numerator and denominator. And of course, we write it so that A and B are relatively prime, For example, we don't write 2 over 6 or 4 over 6. Now he has 2 children, the eldest and the youngest. The eldest is simply A divided by A plus B. The youngest is A plus B divided by B. So the younger child inherits the numerator from the parent. The older child, sorry, the older one. And the younger one inherits the denominator. The sum of the top and the bottom go at the bottom here, at the top here. This is all you have to remember. It's so easy. So let me repeat it 3 times, so you never ever forget. The fraction A over B has 2 children, the old and the younger, the older and the younger. The older is A over A plus B. The younger is A plus B over B. How to remember this? The top of goes here, the bottom goes here. And both of them have the same thing here. The top of the bottom of the young guy is the same thing as the top of the old guy, of the elder. So they're siblings. So let's do a few examples and make sure you understand this, because it's very important to understand this. Of course you understand it. I want you to remember it all your life, at least. It's such a beautiful instruction. So let me make sure you understand. Let me ask you. So 3 over 5 is a fraction. There's 2 children. Let's find out who are the children. Eddie, what's the 2 children of 3 over 5? What's the older child?
3 over 8.
Very good. And Phil, what's the younger?
8 over 5.
Very good. Thank you, Phil. And do another example. 11 over 13. Has 2 children. Yeah. Viraz, what is the older children? The older child?
11 over 24.
Very good. And thank you, Viraz. Yeah. And Mel, what's the other?
24 over 13.
Very good. So that's all you need to know. This is the root for formation. From here, you can construct the whole family tree. Let's do it, but not the whole one, but the very beginning. Let's keep this a human family tree, and let's have the beginning. The first few generations, the creation of the world. The Kalkin will be that naturally generates systematically and beautifully all the possible rational numbers. Not skipping anyone and not repeating. We're going to prove it shortly. It's such a nice, beautiful thing. So first Eve. Eve is 1 over 1. It starts at 1. Then, using this rule, 1 over 2, 2 over 1. Then, 1 over 3, don't tell me, and 3 over 2. 2 over 3, 3 over 1. And if you notice, this side has all integers, and this side has all pure reciprocals. And we keep going, the next generation, 1/4, and then 4 over 3, 3 over 5, and then 5 over 2, 2 over, don't tell me 5, 5 over 3, 3 over 4, 4 over 1. Now, to get the sequence of fractions, all you have to do is read the generations, line by line, generation by generation. First Adam, then Cain, and then Abel, and then so on, Tubal or whatever. So 1 over 1, 1 over 2, 2 over 1, 1 over 3, 3 over 2, 2 over 3, 3 over 1, 1 over 4, 4 over 3. So this is the sequence of fractions. Very shortly we're going to prove that everybody shows up exactly once. It's not like here you say you can have 2 repetitions, and it's not like you forgot somebody. Everybody shows up. But it's a nice feature if you read it left to right. The bottom of this is the top of this. Of course, for brother and sister, for 2 siblings, it's obvious by construction. A over B and A plus B over B. But notice also if you go from here, from first cousin, the oldest of this brother is the same. And even here is the same. So if you read the sequence of fractions, let's spell it out. 1 over 1, 1 over 2, 2 over 1, 1 over 3, 3 over 2, 2 over 3, 3 over 1, 1 over 4. You can encapsulate it into a sequence of integers. The sequence, the famous, starting with sequence of integers. 1, 1, 2, 1, 3, 2, 3, 1, 4. So this is a sequence of integers. That would enable you to construct all the fractions one by one by taking consecutive ratios. 1 over 1, 1 over 2, 2 over 1, 1 over 3, 3 over 2, 2 over 3, 3 over 1, 1 over 4, and so on. Now first, let's convince ourselves in this tree that everybody shows up. But that's not so hard. From this construction, I can easily, you too, can construct the parent. If you call it C over D, so that this is always less than 1, that always bigger than 1. So if I have any given fraction, C over D, everybody is either the younger or the older of his parent. Of its parent, sorry. So if it's C over D, so we can define a function called parent. If C is less than D, if it's less than 1 the fraction, then look here. If this is C, this is D, then it is C over D minus C. If C is bigger than D, it must be an older child. And then the parents is C minus D. So it's a clear-cut function that defines a parent. And every time you have a parent, you have smaller numbers. So later, if you take enough steps, you wind up going to 1 over 1. So you guarantee that everybody shows up. Okay, everybody has a parent, so you can retrace your family lineage all the way to Eve. So this guarantees that everybody shows up. But everybody shows up exactly once. Why not twice? Because if somewhere along this family tree, further down, you have 2 fractions that have show up twice, the parents also must show up twice. And the parent of the parent, and the parent of the parent. But eventually we come to Eve. But Eve is unique. So contradiction, and there's no way that you can have repetitions So this family tree of fractions is guaranteed that everybody shows up exactly once. So this is very nice recursive construction, but can we construct the sequence of the Wilf, the Kalkin Wilf sequence of numbers independently? Yes! Once we realize that every fraction can be written like this in our sequence. For this sequence, using the parenthood, we have b over n divided by b over n plus b of n plus 1. And you have b of n plus 1 over b of n plus 1. But if you look at the family tree, if you count the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the numbers, obviously, in this obvious labeling of numbers, of integers, n to n plus 1. So this must be equal to b over 2n over b over 2n plus 1. And this must be equal to b over 2n plus 1 over b over 2n plus 2. Now we equate and get beautiful recursive formulas. B of 2n equals b of n. B of 2n plus 1 equals b of n. So this is, you can write easily a fast program. Now it's very easy to see, but I won't do it, exercise for you, that this counts something. Suppose you have a country that the coins are 1, 2, 4, 8, 16, 32. Then every amount of money you can only do in one way. This is the binary expansion. But if you are allowed to make change and you're allowed to use it either once or twice, so the generating function is, so the generating function for the binary expansion goes back to Euler. And this is the infinite geometric series. But if you modify it, and you have, so you're allowed, so you can either have 1 penny or 2 copies of the same penny. Then you decide either 2 cents or twice 2 copies of the 2-cent coin. Then you can either have no occurrences of 4 cents, 1 occurrence, or 2 of them. And in general, this infinite product, so to speak, is the generating function for this sequence. It follows from combinatorics. So in Maple or any other, you can quickly have a product and crank out the first 1,000 or 10,000 or even 100,000 terms. So this is my favorite construction. And it's hopefully, not hopefully, but it did make it to proofs from the book. The classic book by Eigner and Ziegler. Proofs from the book. It made it to the current edition for a book, and I completely agree. And it's one of the nicest, if not the nicest, construction. So this is one thing that, by hindsight, is not very deep, but it's so beautiful, and nobody thought about it before. So this is one thing I'd like to share with you. The other thing that personally I like even better, because it made me become a combinatorialist. As you know, combinatorics is a religion, and we all had our epiphany Then we decided the true religion, and we never, like the first love, we never forget. So a long, long time ago, I did something very, very boring, called analysis. I was an analyst. And I didn't exactly like it.